Efficient language models are hitting a fundamental architectural wall. We have linear attention and state space models that process sequences in subquadratic time with constant memory, but they suffer from a critical flaw. They are leaky exact memories. When you ask them to recall a specific fact buried deep in a long context, they forget it. The reason isn't a lack of compute, it's a mismatch in how memory is structured. The human brain solves this exact problem by separating episodic recall from generalization. Today, we're looking at a paper that gives linear attention a biological upgrade, Hippocampal Linear Attention, or HOLA. It recovers exact long context retrieval while keeping O1 memory efficiency, and it does it by listening to the model's own update rules. Let's break down why linear attention forgets. Models like DeltaNet and gated DeltaNet replace the growing key-value cache of a standard transformer with a fixed-size recurrent state matrix. This state is updated online using a delta rule. At each step, the model predicts the next value based on the current state, computes the residual error, and writes that residual back into the state. It's incredibly efficient. But a fixed-size matrix has bounded rank. Once you feed it more distinct key-value associations than its capacity, new writes overwrite old ones along shared key directions. The state becomes a lossy compressor. It's great at distilling general patterns, but terrible at multi-item associative recall or needle-in-a-haystack retrieval. The longer the context, the more the state saturates and the harder it is to recover exact tokens. The authors frame this using complementary learning systems theory from neuroscience. The brain doesn't rely on a single memory system. The neocortex slowly compresses generalizable structure across experiences, while the hippocampus records specific, novel events in one shot and recalls them precisely. If you force the neocortex to handle both, you get catastrophic interference. Efficient language models are missing this complementarity. HOLA formalizes this as a semiparametric test time memory regression. The recurrent state acts as the parametric estimator for linearly compressible structure, while a bounded, exact key-value cache acts as a non-parametric correction for the associations the state can't absorb. This framework forces two critical design questions. What do we store in the cache, and how do we read it? For what to store, most hybrid models just keep the most recent tokens. A sliding window works for local context, but it's useless for a fact that appeared thousands of tokens ago but is still critical. The authors realize the delta rule already computes a perfect selection signal. Every time the state updates, it writes a rank 1 matrix proportional to the write strength beta times the residual norm. This product, beta times the L2 norm of the error, measures exactly how much a token changed the state. A large value means the token brought information the compressed state couldn't predict, and the model actually committed to writing it. That's intrinsic surprise. HOLA uses this magnitude as an eviction score, keeping the top W tokens that caused the largest updates, regardless of their position. It spends the limited exact memory exactly where the state representation is weakest. But storing exact key-value pairs is useless if you read them like another linear summary. If you reuse the backbone's Unitel2 normalized queries and keys for the cache attention, the effective logits are too small. The softmax becomes nearly uniform, and the exact memory degenerates into a lossy soft average. The authors fix this with a sharp readout. They apply a decoupled RMSNorm with a learnable gamma scale to the cache path only. This scales the queries and keys up to a norm of square root of D, which pushes the effective logits into a range where the softmax behaves like a near-argmax retrieval. Crucially, this is decoupled from the state update path. The delta rule mathematically requires unit norm keys to keep its eigenvalues stable and prevent divergence. So the model keeps the original unit norm keys for the recurrent state, but uses the sharpened, RMSNorm-scaled keys exclusively for the exact cache readout. The results are striking. At 340 million parameters, trained on 15 billion tokens, HOLA drops Wikitext perplexity from 27.32 down to 22.92. That's a 16% improvement, and it actually beats a full attention transformer baseline. More importantly, it completely changes long context behavior. On the ruler benchmark, where the standard GDN baseline collapses to near zero recall past 8,000 tokens, HOLA remains highly robust out to 32,000 tokens. It also dramatically improves exact retrieval tasks like FDA and SWDE, while keeping common sense reasoning competitive. The overhead is minimal. The cache is bounded, inference-only state, adding less than 5% peak memory and less than 0.04% to the parameter count. HOLA shows that we don't need to reinvent efficient sequence modeling from scratch. We just need to recognize that a fixed recurrent state is a neocortex, not a complete memory system. By giving it a bounded, exact hippocampus guided by intrinsic surprise and sharpened retrieval, linear attention models finally get the long context recall they were missing. The paper is a clean demonstration of how biological principles, when translated into precise mathematical operations like residual magnitude tracking and decoupled normalization, can solve persistent architectural bottlenecks. If you're working with efficient LMs, state space models, or long context retrieval, this semiparametric memory framework is definitely worth a closer look.